The tensor transformations. Now we're going to talk about how the elements of a tensor must be transformed when we change coordinate systems. For a vector v, we can write in a primed and unprimed coordinate system, vector v is equal to, in the unprimed coordinate system, vi ei hat, and in the primed coordinate system, vi prime ei prime hat. And similarly, for a second rank tensor t, remember that a vector is a first rank tensor. For the second rank tensor t, we have tij ei hat ej hat in the unprimed coordinate system, which is equal to t rs prime er prime es prime hat in the primed coordinate system. Or I could use here tij prime, ei prime, ej prime, doesn't matter. So this is a dummy index. Now if I take this tensor and do a dot product with el hat. So dot product with the tensor t, tij, we have ei hat, ej hat. This is equal to el hat, again dot product with trs prime, er prime hat, es prime hat. Now this is just a matrix element, so that is going to be a number. I can take it out, tij, and what I have here is el hat dot product with ei hat, ej hat. And on the right hand side, similarly, I have trs prime, that's a matrix element. I have el hat dot product with er prime hat, es prime hat. Now, what is this dot product el hat dot ei hat? Because this is an unprimed system, is an orthonormal coordinate system, it's Kronecker delta li ej hat. And on the right hand side, I have trs prime, er prime hat dot product with el hat. Remember, that's just the transformation matrix element arl. This is es prime hat now. Now the Kronecker delta tells us that i's should be replaced with l's. So I'm going to have, instead of tij, tlj ej hat. And here I have trs prime, arl, es prime hat. Now I'm going to take another dot product with em hat. So let's do that. tlj ej hat. And once again, em hat dot product trs prime, arl, es prime hat. And again, tlj is just a matrix element. I have em hat dot product with ej hat. This is equal to trs prime, arl, which is another matrix element, em hat dot product with es prime hat. So I'm left with, because this is again an orthonormal coordinate system, Kronecker delta mj for the dot product em hat and ej hat. And here I have trs prime arl. This is dot product es prime dot product with em, that is asm, the transformation matrix element. Now the Kronecker delta tells us that j's should be replaced with m's. So tlj will become tlm. tlm is equal to TRS prime ARL ASM. So you can see that this is telling you you have an addition over the first index here, and then in the first index of this transformation matrix for the transformation to the unprimed coordinate system. Now, if I continue with this and multiply this with the inverse of this matrix element. So let's call that inverse AKR inverse TLM. This is going to give me TRS prime AKR inverse ARL ASM. Now these are orthonormal coordinate systems, and we have shown that AKR inverse is simply equal to ARK. The inverse of the matrix is equal to its transpose. Multiplied with TLM, this is going to give me TRS prime. Now AKR inverse ARL, this is going to give me a unity matrix, Kronecker delta KL. ASM, which has only non-zero elements along the diagonal. So I obtain ARK TLM is equal to TRS prime. K and L are equal for the right hand side, which is just leaving me with ASM. Okay, now I'm going to multiply it with APS inverse ARK TLM. This will give me TRS prime APS inverse ASM. And once again, I have here APS inverse is equal to ASP. So this is ASP ARK TLM, and APS inverse multiplied with ASM gives me Kronecker delta PM. TRS prime Kronecker delta PM. So I'm left with, this is just multiplication of numbers here. I can just change the order. ARK ASP and T well, at this point here where I had Kronecker delta KL, this L has been replaced with K. Okay, so with the operation of the Kronecker delta. And here I have Kronecker delta PM, which means M will be replaced with P, so TKM will become TKP. And this is equal to TRS prime, so that doesn't affect the right hand side. Okay, now I'm going to call R, L, and S, M. Okay, so this will give me T, L, M prime. R has been called L, S has been called M. Is TKP A, so I have ARK, but R has been replaced with L, so ALK, and ASP becomes AMP. All right, so this means I have, if I recall K as R and P as S now, this is going to become TLM prime is equal to TRS ALR AMS. Okay, now this is telling you that to go from the unprimed coordinate system to the primed coordinate system, I have the additions over the second indices of the transformation matrices. Okay, so we can summarize this result. Going from unprimed to primed coordinate system, Tijk prime is TRST AIR AJS AKT, etc., which is a sum over second index in the transformation matrix. If I go from the unprimed to primed coordinate system, then I have a RI, a SJ, a TK, etc., which is a sum over the first index of the transformation matrix. And how do I find the transformation matrix elements? Aij is EI prime hat dot product with EJ hat, or I can use the transformation equations del xi prime x1 x2 x3 partial derivative with respect to xj gives me Aij. All right. And mixed bases can be used in equations with tensor notation, and this really allows us to work with different coordinate systems. For example, using Ohm's law, I can write the current density. Current density is a vector. In the primed and unprimed coordinate systems, a JI hat or JI prime EI prime hat. And the corresponding electric field, E, can be written as EI hat or EI prime hat in the prime coordinate system. And I have a second rank tensor, the conductivity tensor, which is sigma ij EI hat EJ hat in the unprimed coordinate system, or sigma ij prime EI prime hat EJ prime hat in the primed coordinate system. And then we have Ohm's law, which says that J vector is equal to sigma tensor dot product with the electric field. Now if I apply this, J current density, which is JIEI hat, is, let's write sigma in the primed coordinate system, sigma JK prime EJ prime EK prime hat, and dot product with the electric field written in the unprimed coordinate system, EL hat. This is going to give us sigma JK prime EL. Now I have EJ prime hat and EK prime hat dot product with EL hat, which gives me a transformation matrix. So this is equal to sigma JK prime EL unprimed coordinate system, EJ prime hat, and what I have in parentheses is the transformation matrix element AKL. All right. So you can see that I can work in both coordinate systems in this equation. And for orthonormal coordinate systems, I have to recall that if I take a dot product between EK hat and EL hat, I will end up with Kronecker delta KL. If I take a dot product with EK prime hat and EL hat, I will end up, instead of Kronecker delta, the matrix element, transformation matrix element, AKL. That gives me the transformation matrix. So writing my second rank tensor T as Tijk, or whatever rank it is, EI hat, EJ hat, EK hat, I can handle algebraic operations and coordinate transformations so that a tensor is a coordinate independent geometric object. It's just like a vector. So it's a quantity that's independent of the tensor is independent of what coordinate system I use, or I can handle any algebraic operations with it as long as I recognize these rules for two orthonormal coordinate systems that I'm working with, the unprimed and primed coordinate systems. Okay, so to summarize, we have seen that we can also transform tensors based on what we have learned here. Just by writing our second rank tensor, for example, as Tij, Ei hat, Ej hat, and TRS prime is Er prime hat, Es prime hat, and taking dot products with the unprimed basis vectors, I can isolate the unprimed tensor components here, which becomes TRS prime, ARL, ASM. So you can see that this is a summation over the first indices in the transformation matrix that is going from the primed coordinate system to unprimed coordinate system, sum over first indices in the transformation matrix. When I multiplied it with the inverse of the transformation matrices and also recognize for orthonormal coordinate systems, I'm going to get inverse equal to transpose. I can basically see that the inverse operation is such that the primed components, tensor components, can be obtained by summing over the second index. So TRST, AIR, AJS, AKT, etc. That gives us TIJK, etc. And the transformation matrix elements are obtained by EI prime hat dot EJ hat is AIJ, or del XI prime del XJ from coordinate transformation equations. And these basically transformations allow me to work with either primed or unprimed systems or mixed systems as well. For example, I have written Ohm's law using unprimed components for the current density, primed components for the sigma tensor, and unprimed components for the electric field. Here you can see, if I carefully follow the dot product and the fact that whenever I see EK hat dot EL hat, it's Kronecker delta KL, but EK prime hat dot EL hat is AKL, the transformation matrix, then I will be able to handle this operation with mixed basis. Okay, so this tells us that the tensor written in this notation, we can basically take care of all algebraic operations and coordinate transformations, and the tensor becomes a coordinate independent geometric object, just like a vector.